I now want to define a few special segments when it comes to triangles. The first one I want to look at is the altitudes. Let's suppose we have some triangle ABC. We're then going to let D, E, and F be the feet of the respective vertices of ABC. So I'm going to draw perpendiculars from A to side BC. That would give me point D. From B to side AC, that would give me E. These are all perpendicular. And then the perpendicular from C to side AB. And this would give me point F. So now my altitudes are these segments, AD, BE, and CF. The next segments I want to consider are the medians. Once again, I'm going to start with some generic triangle ABC. I'm then going to look at the midpoints of each of the sides. So let's say here's the midpoint of BC, that'll be L. The midpoint of side AC, this will be M. And the midpoint of side AB will be N. I'm then going to look at these segments, the one from A to L, B to M, and C to N. And these segments right here are going to be the medians. In reality, I didn't draw this perfectly. They should all pass through a single point here in the center, but that's okay. We do get the general idea of these medians. My third segments are going to be angle bisectors. I'm then going to let X, Y, and Z be the points where the angle bisectors meet the sides. So if I try to bisect angle A, this will be point X. Bisecting angle B, so we're cutting all of these angles in half. This would be Y, and then bisecting angle C gives me the point Z. And these segments here are angle bisectors. The last segments I want to consider are the perpendicular bisectors. Once again, I'm going to let L, M, and N be my bisecting points, my midpoints of each side. So there's L, M is about here, and N will be about here. And then we're going to draw the perpendiculars from these points. So there's that one, our next one, and then finally here. And these segments here will be our perpendicular bisectors. While the rest of the things we considered, we specifically looked at the segments. For perpendicular bisectors, I'm going to be actually considering the full line that bisects side AB, the full line bisecting BC, and the full line bisecting side AC. So let's briefly consider only Euclidean geometry, not spherical, just Euclidean. In Euclidean space, all four of these segments will intersect at a common point. So this one wasn't drawn great, but that's okay. And the altitudes do as well. These are all going to intersect at a common point. And each of these points have nice features to go along with them. And it's a good experiment to try to draw some of these on spherical geometry, get a balloon, blow it up, and see about drawing some of these segments and see if you can get these same properties, that all of these different segments are going to intersect at a single point. So we do have a theorem that I won't prove directly, but I will talk about. The angle bisectors of a triangle are concurrent in a point I that lies interior of the triangle and is equidistant from the sides. So if I have any triangle, let's consider this one here, and I look at the angle bisectors. So I'm going to go ahead and bisect all of my angles, at least approximately, the best I can do. What we know, what this theorem tells us, the first thing is that all of these angle bisectors are going to intersect at a single point. Right here, this is my point I. The next thing it tells me is that this point will always be inside of the triangle. Even for an obtuse triangle, it's impossible to get this point outside of the triangle. And the other thing is the distance from I to each side, if I actually look at the perpendiculars, is going to be the same. So the distance from I to each side will be the same. And this allows me to actually be able to draw a circle. See if we can get this scaled right. It needs to be able to be centered at I and pass through all three of those points. So this circle right here is known as the incircle. It is the largest circle that can be contained inside of this triangle, and it will have this point I that we are talking about here as its center. Our next big result is if we look at the perpendicular bisector of the sides of a triangle, then they are going to be concurrent at a point I, or a point O, that is equidistant from the vertices, provided any two of them intersect. So we want to actually bisect each of these segments perpendicularly. So here's my first one. If I try to bisect this side perpendicularly, it'll be about right here. And finally, this last one will go about right here. So not perfect, but that's okay. We have our point of concurrency right here. And we call this point O. And not only do they intersect at a point, but if I consider the distance from this point to each one of my vertices, it will be the same. And so this can allow me to once again draw a circle, since the definition of a circle would be this idea of points being the same. And I didn't draw my picture great because this looks a lot more like an ellipse, but that's okay. The idea being we should have a circle with center O that passes through each one of the vertices, and this is called the circumcircle. It is the smallest circle that actually contains this triangle. So let's look at these two ideas very quickly. Here is a general triangle. We are going to start here by drawing the angle bisectors. We can see that they will intersect at our point I, and if I draw the circle centered at I, it's going to intersect my sides perfectly. This would be our incircle. And if I grab one of these vertices and I move this around, we can see that it changes accordingly, but no matter how I make my triangle, this is going to work. I can still have this circle centered at I that is completely contained inside the triangle and is tangent to all of the sides of the triangle. This one here looks at my circumcircle. So these points L, M, and N are the bisectors. It's the midpoint of each of these sides. If we draw up our perpendicular bisectors, we can see that they will all intersect at a point, and if I draw a circle centered at that point, I can get it to pass through all of my vertices. Let's move this point B in a little bit so we can see the full circle. But we can see once again that no matter how these points change, this circle will still pass through all of the vertices and still be centered at this point O, where the perpendicular bisectors intersect.